Hello, everyone. Today we'll be discussing the solution to problem one of the USACO February 2026 Gold Contest. And in this problem, you're given a permutation P of length n, and you'll define a function f of P, which essentially takes the sum of the absolute difference between P sub I and I divided by 2 over all indexes I from 1 to n. And you'll call this permutation good if and only if it can be sorted with f of P or less swaps of adjacent elements. And your goal is to determine which cyclic shifts of P are good. So for example, we have this permutation, which is 1, 2, 4, 3, and there are four cyclic shifts. So the first cyclic shift is if we do nothing. So you have the original permutation. And if we did calculate what f of P is, we get 1 minus 1, which is 0, and then 2 minus 2, which is 0. And then we have 4 minus 3, which is 1, divided by 2. And we have 3 minus 4, which is negative 1, but we take the absolute value. So we also get 1 half here. So add it all together, and f of P is 1. And we can sort this permutation with one swap. We just swap the 4 and the 3. So this permutation would be good. And now if we shift this entire permutation by 1, we get 3, 1, 2, 4. And so if we recalculate f of P, we have 3 minus 1, which is 2 over 2. And then we have 1 minus 2, which is negative 1 over 2. And we also have 2 minus 3, which is negative 1 over 2. So if you add up the absolute values, you get 1 plus 1 half plus 1 half, which is 2. And you can sort this permutation in two swaps. You can swap the 3 and the 1, and then the 3 and the 2. So this permutation is also good. On the other hand, the other two shifts are not good. So we can see if we shift it twice, we get 4, 3, 1, 2. And if we calculate f of P, we get 4. But it's not possible to sort this permutation with four swaps of adjacent elements. We can try doing it, but we'll end up one swap short. And similarly, for like the last shift of 3, we have 2, 4, 3, 1, and f of P is 3. And it's not possible to sort this permutation with three adjacent swaps. The closest we can get is like where we just need one more swap, but we're not able to fully sort it. So therefore, the answer to this test case would be 0 and 1, and not 2 or 3. There's only two good valid shifts. Okay, so now let's see how we can approach the solution to this problem. And there are several different solutions to this problem, but here I'll describe one which was most intuitive for me. So the first observation we'll want to make is that we can intuitively interpret the like absolute value of P sub I minus I to be the distance of that element P sub I from its final location in the sorted array. So since P is a permutation, the value of like P sub I is like the final location in the sorted array. So this difference is like the distance between its current location at index I and its final location at index P sub I. And now we can look at f of P, and we can notice that each swap that we make in adjacent elements can bring at most two elements one step closer to the final location, right? Since we'll swap two elements, and in the best case scenario, we'll bring both of them closer to the final location. So what this means is f of P is a tight lower bound on the number of adjacent swaps needed. We can never use less than f of P swaps. And this is because f of P represents the total distance of all elements from their final locations divided by 2. So since each swap can only bring at most two elements closer, the minimum number of swaps we can use is f of P. So therefore, like we have to achieve this lower bound in order for the permutation to be good. And so every swap that we make has to bring two elements strictly closer to their final location. Yeah, in other words, we cannot waste a single swap. Like we have to be as efficient as possible. Otherwise, if we're forced to waste a swap, then the permutation is not good. So we can come up with some conditions for this, right? The first condition we can think of is that if we have like the set of elements that are moving right to get to their final locations, so the set of elements which are currently like to the left of their final locations, these elements have to retain their relative order. And that is like one of these elements can't overtake the other one, because if that occurs, the element that is overtaken is like wasting a swap moving backwards. And because we can't waste swaps, that means the permutation is not good. So therefore, like all elements that are moving right must already be in like the correct relative order. And this also applies for all elements which are moving to the left. Also, we have the condition that if the element is already in its final position, so if P sub I equals I, then it can't move at all. If it moves at all, we'll have to waste time bringing it back. And again, we can't waste any swaps. So elements in their final position have to remain fixed. And this is a slightly like clunky way of saying this condition, which needs to be true. Uh, so we can actually reframe our condition into the following form. Yeah, we can write it as follows. Essentially, we can say that subsequence consisting of all elements which are greater than their indexes I must be increasing. And the subsequence consisting of all elements like p sub I less than or equal to I is also increasing. So what this means, the elements where p sub I is greater than or equal to I is the set of elements whose final locations is like the current index they're on or an index that is greater to the right. And similarly for like p sub I less than or equal to I, it's all elements which are currently at their final location or their final location is to the left. And what it means for these sequences to be increasing is that if these sequences are increasing, that means they are in the correct relative order to their like final locations. So if the sequence was not increasing, that means there's an inversion where one of the elements has to move farther and overtake another element to reach the final position, which again we said is not allowed because we don't want to waste any swaps. And therefore, these two conditions describe like the condition in the previous observation. So these two are equivalent, but this one is easier to work with, as we'll see later. And we can show that if these two conditions are met, there is always a valid swap, which will bring two elements closer. There's always going to be a valid swap where like we can swap two elements and it will bring like both elements one step closer to their final destinations. So this is a necessary and sufficient condition. Okay. So now we know how to find the answer, at least for one permutation, but we want to find the answer for all cyclic shifts of that permutation, right? And so one thing we can do is think about how do these subsequences, which we've described here, change between cyclic shifts. And so in a cyclic shift, what we're essentially doing is we're removing an element from the right end of the array and adding it back to the left end. And every other element is going to be shifting one to the right. And so we can notice that each element is going to be like added or removed from a subsequence at most two times, right? So the one time is going to be when it's going to be moved from the right end to the left end. So obviously it's going to change like its index and it's going to change which subsequence it's in. And the other time that it changes which subsequence it's in is when it reaches like when it becomes a fixed point. So when it reaches its final location as we like shift it one to the right each time as we go through each cyclic shift. And the reason is after this point, if we shift it further to the right, um, it will move to the left and it will no longer be part of like uh it's going to transition from moving to the right to get its final location and moving to the left. So it will like leave one of the subsequence and go to the other subsequence, which is why this is also like an important point to consider. But other than these two like moments, each element is going to stay in the same subsequence it's in. So there's actually O of n times that we have to add to or remove to a subsequence. And now that we know there's only O of n like additions and removals, we can think about how can we efficiently like maintain whether or not this subsequence is sorted. Yeah, so we need to handle add mover operations and we also need to check if its subsequence is increasing. And we can notice that we can like write the condition of subsequence increasing as checking the number of indexes where like a sub I is less than a sub I plus one. So essentially, if like the number of adjacent elements which are sorted, and if that number is equal to the length minus one, then the entire sequence is sorted. So if all pairs of adjacent elements are sorted, then the entire sequence is sorted. So using this fact, we can write a data structure which will like handle this for us. So we can store a subsequence as a set of pairs of the index and the element. And essentially we can add or remove to this subsequence. And we're going to maintain like the count of adjacent indexes where a sub I is less than a sub I plus one. So if we're adding or deleting, if we're adding, we're just going to look at the two adjacent elements next to the element we're adding in the set, and we'll update the count based on if this condition is satisfied or not. And then to check whether or not it's increasing, we'll just check if the count is equal to like the total size of the subsequence minus one. So if all pairs of these adjacent elements are increasing. So this gives us our solution, which we can implement in C++. So right here, I have code which will read in the input, and we're using fast IO to speed up the input and output. And right now, the first thing we'll do is we'll create our sets, our sequences. So we'll create a sequence where like pi is less than or equal to I, and we'll create a sequence where pi is greater than or equal to I. And these will be like the count of like the number of adjacent elements which are in the correct order. And we can define functions which add or remove to the sequence. Okay, so now we can define a function where essentially we'll define a lambda function which will add to one of our sequences. And using iterators, we can essentially find before we add it, like the what would be the previous and the next element. So that'd be nx and pr. And if they are currently like adding, contributing to our count, we will subtract that. Since after we add this new element, they will no longer be adjacent. And then we'll insert our new element into the set. And we'll update our count. So we'll find a new element and we'll look at its previous element and we'll look at the element after it. And if each of these are in the right order, in increasing order, we'll add one to our count for each of those. And then we can also define a function to remove an element from our sequence. So we'll first find the element and we'll update if like with the elements to the left and the right, and we'll subtract the contributions if they are in the right order. Then we'll remove the element and we'll add back the contribution of like the two elements like which are now adjacent after we remove this element. So essentially like the same process for adding but in reverse. And then finally we can have a function to check if this sequence is sorted or not. We'll compare like the sequence size to like the count of adjacent elements which are sorted. And this is essentially our data structure, which will allow us to solve the problem. Okay. Next, we need to find like the moment at which each element becomes a fixed point. So at which cyclic shift does an element become a fixed point? Because at this point, we'll have to like transition the element into different sequences. So essentially, there's two cases where either the element is going to reach its fixed, like it's going to reach its like fixed point without having to cycle back to the beginning of the array. So that's the first case. Otherwise, we have to account for the fact that it will go from the rightmost endpoint to the leftmost endpoint of the array and then reach its fixed point, which we can account for like this. And this just stores the time at which each of these elements becomes a fixed point. And now we can initialize our sequences. So for the initial array without any cyclic shift, um, if p sub I is less than or equal to I, we add it to the sequence of less. And if it's greater than or equal to I, we add to the sequence of more. And you can notice that if p sub I is equal to I, then we add it to both sequences, as we described before. And then now we can loop through uh, each of the cyclic shifts from 0 to n minus 1. And we can now like add it to our answer if it's good. So the first thing we do is we'll check if it's good by checking if both sequences are sorted. If it is, we can add it to our answer. And then the rest of the for loop is updating it for the next iteration. So if we're done, if this is our last iteration, we don't need to update, so we can just break. But otherwise, we might need to add or remove to some subsequences. So what we can do is first, we're going to remove from the sequence which is more every like element which just crosses past its fixed point. So we'll loop through the current fixed point and we'll remove every element which is past that. And then we'll update the rightmost element. So we'll move it from the rightmost point to the leftmost point and we'll update the sequences it's in. And then finally, if on the next iteration, uh, elements are going to start to reach their fixed point. So essentially on the I plus one iteration, if elements reach their fixed point, we're going to add it to the sequence with less. And after this, we've fully updated our like sequences for the next iteration. So on the next iteration of the for loop, we can just check if those are sorted. And if they are, we can add that to our answer. After this for loop is done, our answer will contain like all the good cyclic shifts. And all we'll need to do is print out our answer. Okay, so that concludes our code, and we can now test it on the test case, sample test case. So here we have the sample test case from USACO, and we'll see that when we run it, we do get the right answer. And this code will get full credit for this problem. Thank you guys for watching. I hope you guys learned something from this video.